So our next speaker is going to be Ken Shan, and he is going to be talking about some work that they've been doing on calculating distributions, which from the title I'm guessing is related to the Hikaru system.
Yes.
Yes, as was mentioned earlier in John's talk.
Yes. Sorry, let me, okay. All right. I actually, in the interest of time, decided to change my talk a little bit in two ways. First of all, I decided to drop all the occurrences of the word guys in my talk, which shaved off a few minutes. But that was still not enough, so I also decided to talk about part of what I was going to talk about originally. Okay, so I'm extremely excited about this particular part because, like with Frank Wood's case, we're also about to get a paper rejected. And so the overall story I was going to tell is about a bunch of operations that we've been building in our group that performed exact calculations on probability distributions. And even though these are exact calculations, the operations can be used to express a variety of approximation strategies that you might use. So of course, nowadays there's a very famous instance of such an exact calculation, and that is automatic differentiation, which can be used to express gradient descent. Now remember that automatic differentiation is exact, but it allows you to express more easily approximation algorithms such as gradient descent. Now I'm not talking about automatic differentiation today. Instead, I'm going to talk about one of two operations we've been building to calculate on probability distributions. So what I'm not going to talk about mostly is automatic simplification. That just means something that will take a probabilistic program and return a simpler program that might have some variables integrated out, maybe some conjugacy relations recognized, but it's going to denote the same measure or the same kernel. What I am going to mostly talk about is automatic disintegration, and that is, well, I will explain what it is, but you can use it to express a variety of inference and sampling tasks. And the most exciting thing that is about to get rejected is a paper about how we extended disintegration to deal with a broader variety of base measures. Okay, so overall the story is about calculation. So but before I launch into the details, I want to give you another view about calculations that I also find very compelling. And that view is provided by Ben de la Creme, who wrote, if being calculating is thinking through your words and actions and modeling the behavior you would like to see in the world, even when it is difficult, then I hope more of you will become calculating. So like her, I also hope that you will become calculating, and I also want to note that she also expresses a separation between modeling and inference. Okay, so now let's come back to automatic disintegration. What is disintegration? Well, on one hand, disintegration is a mathematical notion that relates a bunch of measures. What does it relate? Well, it's basically an equation between the two probabilistic programs I'm showing on each side of the equal sign. So on one hand, we have a joint measure. So let's say you have some kind of program that, when run, will sample a pair. The pair has the type t times p. So t here is some kind of, you can think of it as an observation that you're going to make, some kind of index. And then P is what you want to infer, what you actually care about predicting, perhaps. So suppose you have such a program. Well, what disintegration means is that this program could be rewritten to an equivalent program, which has two parts. The first part is a base measure that is just a way to draw a T, and then a kernel is just, of course, a function that takes this T as input and returns a measure over P, which is the second part of the pair. Okay, so all that disintegration says is that the left-hand side is going to be equal to the right-hand side. So if you have a program that somewhere in it draws T and somewhere else in it draws P, then disintegration means let's try to write it as some program that first draws T and then draws everything else. So somehow we're going to move the drawing of T to the top of the program. And once we move the drawing of T to the top of the program, it becomes easier to use this measure for a lot of inference tasks. And there are two inference tasks in particular that is generalized by disintegration. The first is to find the density of one measure with respect to another. So here we have an example where the normal distribution has a density d norm with respect to the Lebesgue measure. And one way to treat this as an instance of disintegration is that mu could be the process of drawing t from a normal distribution, and then p is actually nothing. Just put the empty data structure in p. Okay, the unit type is p, and that is equivalent to a different program which starts by quote unquote drawing t from the Lebesgue measure, and then scores that t by the density of normal. Okay, so that's one example of how disintegration generalizes density. And also, you can see the picture, in the picture of what I've shown is that on the left-hand side, you have the normal distribution. On the right-hand side, we've kind of chopped it up into a bunch of vertical bars, right? Because on the right-hand side, what we have is for each value of t, we have a measure over the unit type. And that is to say, we have computed the density of the normal distribution at that point. Okay. Another thing that disintegration generalizes is conditioning. So for example, you might have a two-dimensional distribution. That's the distribution on the left. And it's defined first by sampling x and y from the standard normal, and then computing some kind of linear combination of x and y. So you could think of this as either some kind of noisy observation of x, or you could think of it as, well, maybe x and y are velocities of two particles in one-dimensional space, and t is like the total momentum of the two particles. But anyway, suppose that this total momentum or this noisy observation is what you measure. So you want to condition on t to perform a belief update, right? So what we're kind of trying to do then is to take this distribution, this two-dimensional distribution picture on the left, and chop it up into slices indexed by t. And so on the right, each slice is a slice along which the value of t is constant. So each slice corresponds to a value of t, and we might want to find a function that maps each value of t to that slice, which is a distribution over x and y. And that's what disintegration is. And so you can think of this integration as a kind of unnormalized conditioning. It is unnormalized because, as you can see, the slices on the right don't all have the same size. We could normalize it. So I've just normalized the slices, and then yes, you get a kind of conditioning, but in the many cases where you don't really care if your conditional distributions are normalized or not, it actually turns out to be easier to just compute the unnormalized conditional distributions, and that's exactly what disintegration is. It's not even it's generalized by disintegration, it is disintegration. Okay, so to summarize, disintegration is a mathematical notion that relates a bunch of measures that generalizes density and conditioning, and it can be thought of as unnormalized conditioning. But it turns out that you can also use disintegration as a program transformation. It turns out to be a semantics preserving transformation on probabilistic programs. So when I say probabilistic, like everyone else here, I think, we mean a probabilistic program, of some kind of program that can perform a kind of random choice that has scores associated with it. So you've seen a random choice so far, like in the normal, and also you've seen, sorry, should I go farther or closer? Further, oh, I'm sorry, I keep trying to get closer. Wow. This is exactly the kind of gradient descent problem that we were seeing earlier. Okay. Thank you. So the score, yeah, you're also seeing a scoring part of the probabilistic language I was showing earlier. Okay, what are programs? So remember that a program can be a sequence of operations, and the operations could be random or deterministic. It's not just a primitive. So for example, we're able to find the density or unnormalized conditioning of a sequence of operations with respect to another sequence of operations. And this morning, Stuart Russell mentioned that it's important to be able to condition on the sum of a bunch of random variables, and this is an instance because summing could be the last in the sequence of operations. Okay, and finally, I just want to give a shout out for what we mean by semantics. We mean S-finite measures or kernels, and that's a special case of measures and kernels that reflects a certain kind of invariant that's maintained in in many probabilistic programming languages. Okay. So not only can we treat disintegration as a semantics preserving program transformation, this transformation can be derived by equational reasoning, which means that you can write down what you want, which is at the top of the screen, and then just think through all the possible constructs that you have in your probabilistic language. And for each case, you write down the corresponding case in your program transformation, and you'll be done. And as part of deriving what your transformation should do, you would have proven it's sound. Okay, so when I say proving it sound, I mean that we don't always successfully find a disintegration. Sometimes we just say, sorry, I don't know if there is one, but we don't have one for you. But if we do say there is one, we give one to you, we know it's correct because of this equational derivation. Okay, now in this talk, I'm not going to show you the equational derivation. The reviewers didn't want to see them either. So what I'm going to show you instead is a couple of example programs where we perform the same kind of equation reasoning by hand that is performed by the program transformation. Okay, so the gap between the concrete cases I want to show you and the general case that's implemented in the transformation is what was described yesterday as some smart PL rewriting. And in here, just to be more specific, we have kind of a lazy form of partial evaluation, which you can think of as a way to traverse a stochastic computation graph. Okay, so commercial time, again, just to remember, if you're into this sort of stuff, then you should really come hang out at POPO, and especially at a workshop right before POPO next January. Again, submission deadline is November 1st. And this is a very informal workshop, and POPO folks are very keen to talk to people in this room, so I hope you all come. All right. So let me start with an example of disintegration where we already know what the base measure is, and this is basically before this year that we know how to do. Okay, so this program is the same as before. We have a linear combination of two standard normal distributed random variables, and we want to slice the distribution along an index, which is t, and that's a linear combination of the two. Okay, so sorry. Oops. Why did it go back? Okay. Okay. So on the right, we have the goal, right? The goal is to fill in what is a p distribution, what is a yellow thing that we can fill in to make the equation come true. And it turns out that in 2 steps, we can show a p that makes the equation come true. And the 2 steps correspond to 2 very familiar ways that I think people reason about probability distributions. The first way is to look up a density of a measure. So if you see a normal distribution, then you can just go to Wikipedia and look up what the density is of the normal distribution with respect to the Lebesgue measure. Okay, so that's the left-hand side step. And then on the right, you have what we call reparametrizing. And it's the same reparametrizing as when you say reparameterization trick. It is basically, I think of it as changing the integration variable of an integral. So it's on the left-hand side of the reparametrization. Let's see if this works. Anyway, in the middle, you have integral over y, and then inside that you define t in terms of y. On the right-hand side, we have an integral over t at the top. So we have successfully disintegrated the program, and then y is defined in terms of t rather than defining t in terms of y. Okay, and then there's a Jacobian correction, which here is just a factor of 10. Okay, so these are the 2 steps are found by the disintegrator. Now, when the disintegrator is trying to look for this kind of equational derivation, it's actually working from right to left because it's working from the goal backward to say, oh, if I could somehow come up with something that I could then reparameterize, then I'll be done. Okay, great. So how am I going to come up with the middle part? Oh, that's just a density lookup. So it's actually coming out with this derivation kind of in some sense from right to left and then filling it in to complete it. Okay, so that's a starting point. We knew how to do this a year ago. And this is also the topic of some other papers where we knew how to, for example, find the density of a probabilistic program with respect to a base measure that's built up using the Lebesgue measure several years ago, I guess 6 years ago. And now there's been 2 extensions. We've been extending that to arrays whose size is unknown, so that's exciting because it's actually very much exercising symbolic computation. And so what I want to again focus on today is that we've extended the language of base measures some more to include a broader variety of base measures. And this variety has a bunch of applications that I've tried to group into 2 groups. So on one hand, you have applications in the form of what if there's some kind of clamping or censoring in your observation. So this is the famous GPA problem, the Tobit model, or the way I like to think about it is an instance of camera over or under exposure. Another application category is to use this kind of disintegration to model certain forms of metropolis Hastings sampling, such as single-side image and also reversible jump, and also applications to graphics. Okay, so in the rest of the talk, I just want to give you an overview of how we deal with a particular case of these applications, which is what if you have a clamped observation and you want to perform a belief update. And because the observation is clamped, the marginal of the observation is no longer continuous with respect to the Lebesgue measure, so instead we have to use a base measure that is a mixture of some discrete and continuous distributions. Okay, so this is a problem. Suppose that we don't observe t. Instead, we observe t prime, which is just clamping t to between -3 and +3, because the whatever machine we use to measure t is limited between -3 and +3. So if t is actually -5, then t prime is going to be -3. We can no longer express this probabilistic program on the left as anything that begins by drawing t prime from the Lebesgue measure. There's just no way to chop it up that way. So instead, what is the base measure we should use? Well, we can get a hint by rewriting the program into the sum of 3 programs, basically treating the 3 possible ways of clamping or not clamping as 3 components of a mixture, right? So the program is really a mixture of drawing a t that's too small and returning -3, that's one Dirac. Drawing a t that's too big, I'm sorry, the lesson should be greater than there, and then returning +3, or just actually drawing a t that's in range and returning actual t. So because each of these components can be disintegrated with respect to a discrete or continuous distribution, we can mix the components by mixing the base measures. So it turns out that it is possible to disintegrate the left-hand side with respect to the right-hand side base measure, which is a mixture of a Dirac at -3, a Dirac at +3, and the Lebesgue measure. And we can do that by separately disintegrating each component using the same sequence of equational reasoning steps as you've seen before. The code is a bit longer, but we've just by equational derivation, it's not that hard to figure out how to carry out these steps. Okay. Now, of course, we don't really want any probabilistic programmer to have to write down that base measure. It's already getting long, and when you're using this to do MH, like single-side MH, it gets even longer. So instead, we want to infer the base measure, not just check it. And this feels kind of like a type inference problem, and we managed to solve it in the same way as type inference problems are typically solved for programming languages. So we introduce a base measure variable that is the capital typewriter font B that you see on the right. So we don't know what this variable B is. It's some kind of base measure. We're just going to treat it symbolically, and we're going to continue to disintegrate these 2 mixture components. And it turns out that we managed to do it, and in the result, there's a lot of symbolic dependencies on this base measure variable B. And in particular, we have to refer to some density that the Dirac measures and the Lebesgue measure better have with respect to this unknown base measure B. So we can collect these symbolic densities and treat them as constraints on the base measure variable B to say, well, whatever the base measure B is, it better be some measure with respect to which these 3 measures have a density. And we just take a kind of a lattice, meter join, or whatever it is, and we find that the principal base measure is a mixture of these 3 components. Okay. So just to conclude, I've told you about disintegration both as a mathematical notion and as a program transformation, which we've recently extended to a broader variety of base measures, including mixtures of discrete and continuous components, as well as I didn't talk about disjoint sums, and I didn't talk about dependent products. And these base measures can be not just checked, but also inferred. Now, usually I will stop here because this is a conclusion slide, but I also want to show you something that I think maybe everyone in this room, or at least some people in this room, should like to work on. And that, so treat this science fiction paragraph as a kind of grand challenge for AI or probabilistic programming. Here is a computer that responds to a question involving a fuzzy edge concept, not by rejecting the vague question, not by giving an overly precise answer, but by giving a vague answer and offering options to continue conversation. So, thank you.
A question. Any question?
I think I want to know why your paper was rejected.
Oh, you seriously do? I mean, I don't see any whiskey around.
Question of offline, but yes,
Yeah.
I'm interested to hear this.
Well, okay, so, no, but I'll tell you, I mean, here's another call for help. What? No, it's fine. Well, I don't think so. Okay. Anyway, so here's a call for help. I think this is one major reason is that it's hard to evaluate what we've done. Especially, it's hard to evaluate the completeness of the algorithm because we don't have a lot of examples of these programs being written because nobody wants to write these programs because no system would deal with these programs, right? So how do we have to build up a corpus of programs that have yet to be written, basically, because it's not today useful to write them. So that's one of the major challenges.
Yeah, I mean, and to build on that comment, I think that does actually motivate the development of standard benchmarks, certainly
Right.
in the PL community.
Right. Even
This
if
is
they
something
don't
that
work,
we use.
especially if they don't work.
Yeah, so just to fill in a little bit of detail, the famous GPA example that you mentioned was rejected 5 times. So it's no wonder
Okay.
no one can find any programs
4 more
with
times.
these examples.
Thank you.
All right. Well, we'll take one more, but we're running into our break. Okay, all right. We will come back at 4:45, so it'll leave us 9-10 minutes, and then we'll return for our next session on language and systems.